Hello, welcome to the another lecture of control system. I am Prajit from Asansol Engineering College. Like to discuss about some ideas about state-based model. Already I have been discussed from lecture 1 to lecture 9 respectively. What is control system? What are the types of control system, that is open loop control system, and what is the relevant example, and what is closed loop control system and what is its relevant example we have been discussed. Besides, I already mentioned what is transfer function, what is the how can we generate a transfer function with the help of block diagram reduction rule, how can we generate transfer function with the help of signal flow graph, that is the even I have been mentioned, that is the Mason's gain rule for SFG, that means signal flow graph reduction, and why SFG is more beneficial with respect to block diagram, that is also illustrated. Besides, we have been determining the transfer function of an electrical circuit for RLC network, RLC series, RLC parallel, mixed mode, whatever else it may be. Even we have been determined the transfer function for a mechanical system, for mass spring system, even for electromechanical system. And we already discussed about the analogous system. Analogous system means, suppose I am giving you one mechanical equivalent circuit, and how can we generate an equivalent electrical circuit for the same scenario, that means with the help of force voltage analogy either, or with the help of force current analogy. Similarly, for rotational mechanical system, we can generate for rotational mechanics, if a mechanical system, if we are giving you, and how to generate an electrical circuit with the help of torque voltage analogy or with the help of torque current analogy. Besides, I have been discussed about the transfer function of a DC motor with fixed armature current and DC motor with fixed field, that is the with field control DC motor with fixed armature current, and that is the armature control DC motor with fixed field. Already I have been discussed. Even the transfer function of a room temperature controller is already derived for that. Even I have been mentioned about the state space model, what is state, what is space, how to model a equation, and what are the respective example for that, and how to evaluate state transition matrix, and that thing is already evaluated. State transition matrix is nothing, we have been denoted by phi of t, and that is again we can represent it as a e to the power, that is exponential at. A is a system matrix whose dimension is always square matrix, that is n cross n, and we know how to evaluate the solution of a state equation for homogeneous case as well as for non-homogeneous case, that is also mentioned. Even the properties of state transition matrix is also mentioned for that. Today I will discuss about the transfer function of a state model. Okay, so see, starting from the initial problem, and already we have been discussed about the state space model for that, and this is the governing expression, that is y dot n, that is state space representation of a canonical form. I have already discussed that thing on the previous slides, where I have been mentioned the system is defined as y dot n plus a1 y dot n minus 1 plus 1 dot it a n minus 1 y dot plus a n y is equal to, actually I have been mentioned there only u. Now see, right hand side contains not only u, that is the nth order of u, b0 u of n plus b1 u of n minus 1 plus 1 dot 8 plus sorry bn minus 1 u plus, and that is the u dot the plus bn into u. In such a way we can generate the system. Now where u is my control unit, control input, and y is my output, and we can write the equation in such a way that y of s by u of s. You may ask me, sir, how it has been written from the differential equation? When I have been applied the Laplace transform with zero initial condition. Why zero initial condition? Because my aim, I need to determine the transfer function, that's why. So when I am using Laplace transform on both sides of the equation, above equation number 1 with 0 initial condition, it generates y of s by u of s is equal to b0 sn plus b1 s to the power n minus 1 plus 1 dotted bn minus 1 s plus bn divided by s to the power n plus a1 s to the power n minus 1 plus 1 dotted an minus 1 s plus an. Equation number, we shall represent state space representation of the system defined by equation 1 and 2 in controllable canonical form, observable canonical form and diagonal canonical form, and one by one we will see how can we generate controllable canonical form. See, we consider the following state space representation being called as a controllable canonical form. Means, see, we are taking the nth dimensional equation, that is x1 dot column wise, x1 dot x2 dot so on dot xn minus 1 dot up to xn dot, and A matrix is nothing that is square matrix. See, there we have been mentioned x1, this model is already illustrated on the previous slides. Taking help from the previous slide, I am mentioning that thing. And here, see, there we have been mentioned y is equal to x1 and x1 dot is equal to nothing, that is x2. Okay, so see here what thing, x1 dot is equal to only x2. See, x1 dot is equal to x2, that's why 1 is coming, rest elements are 0, and x2 dot is nothing, that is x3. In such a way it will be going on. So see, and the last row of the A matrix contains the coefficients are minus an minus a suffix n minus 1 minus a suffix n minus 2 so on dotted minus a1, and the state variables are x1 x2 so on dotted xn minus 1 and xn. And control matrix, that is the B matrix, is the row matrix, that is only one column and n row, that is n cross 1 dimension. See, since the I have been mentioned there that equation contained only u term, that's why see only u is available, that means the last row contains one element and rest elements of that particular column of the B matrix is 0. Now taking help from the above equation, we can formulate the expression of y in such a way, y is equal to bn minus an b0, bn minus 1 in minus an minus 1 into b0 so on dot 8 up to, this is the output matrix. See, this matrix is generated as C matrix. Okay, keep in your mind, C matrix can be written as in such a way, up to b1 minus a1 into b0, and the X matrix is nothing, x1 x2 so on dotted xn, that is n state variables plus b0 into u. Okay, so this thing should be in your mind. See, C matrix is nothing, that is this one, that should be in your mind. And this is the main formula. With the help of this C matrix, we can generate the transfer function of a state model. We will see on subsequent example. Note that the controllable canonical form is important in discussing the pole placement approach to control system design. So, where the pole placement is needed, we can apply the controllable canonical form. Okay. Now see, observable means what things are happening there. Observable means see, C will be replaced by B matrix. The C matrices, matrix terms, whatever the terms are available, whatever the data are available, that will be available at the B matrix column wise. Then we can say that is the observable means that is after performing the experiment, we can observe that thing. That means the C matrix will be transpose nature to the B matrix. See, we can consider the following state space representation being called an observable canonical form as, see, this left hand side is remaining same, that is x1 dot x2 dot so on dot xn dot is equal to 0 0, because A is transpose. Observable means all the matrices will become a transpose nature. See, A becomes A transpose, that's why this thing is happening. 0 column is 0 1 0 so on dotted 0, then second column is 0 0 1 in such a way, because that A is becoming transpose A, whatever the original A that is available to the controllable matrix, for observable matrix A becomes a transposable matrix, A becomes a transpose. That's why that variable, that datas are remaining changed, rows becomes column and column becomes rows for the transpose nature. And see, whatever things have been mentioned, the output matrix C matrix contains the B elements, B matrix elements, whatever things are available for controllable part, because that was transpose. That means there B, here B transpose is equal to C and C transpose is equal to B, and whatever the C matrix was there, that is available to the C transpose matrix is available to the B. That means we can write as Bn minus, in the B control matrix contains Bn minus A n B0, Bn minus 1 minus n minus 1 into B0, so on dotted B1 minus A1 into B0 whole into U. This matrix is known as the control matrix or input matrix, that is B matrix, and C matrix is nothing, that is output matrix. Okay. Now diagonal canonical form greatly simplifies the task of computing the analytical solution to the response to initial conditions. We here consider the transfer function system given by equation 2. What is the equation 2? That thing we will see. This is the transfer function, obviously. So equation 2, we have the case where the denominator polynomial, obviously denominator polynomial involves only distinct roots, and for the distinct root case we can write equation 2 in the form of y of s by u of s is equal to, see, numerator will remain unchanged, that is b0 sn plus b1 s to the power n minus 1 plus so on dotted bn minus 1 s plus bn, divided by roots means that should be mentioned p1 p2 so on p up to pn will be the roots, that means poles, nothing. So we can write as s plus p1 into s plus p2 so on dotted s plus p1, and with the help of partial fraction nature we may write as b0 plus c1 by s plus p1 plus c2 by s plus p2 plus so on dotted cn by s plus pn, c1 c2 cn are respective constants. Okay, we can represent it in such a way. So diagonal canonical form can be represented as, for the state space representation, C x1 dot x2 dot so on dot x dot n minus 1 and x dot n is equal to, see, all the roots, that is minus p1 minus p2 so on dot n minus pn, those roots will be arranged in diagonalized fashion for matrix A. That A matrix means system matrix A whose dimension is n cross n, that is square matrix, and rest elements are 0. Whereas, and state variables are mentioned x1 to xn, whereas all the input variables, input matrix variable, that is B matrix variables, are always 1. And C output matrix y is equal to c1 c2 so on dotted cn minus 1 cn. That means this numerator, coefficients of the numerator term will be available for output matrix, that is c1 c2 so on dotted cn minus 1 cn, and state variables are remaining plus b0 into u, because b0 is available here in isolated approach, that's why b0 into u is available, that is d, b0 is d matrix. Okay, d into u. Now directly we are coming to the problem. Obtain the state space representation for the transfer function system. This is the equation 16 in the controllable canonical form. G of s is equal to s square plus 3s plus 3 by s square plus 2s plus 1. See, we should take help from the, because this is the controllable canonical form, we should take help from this formula. That means y is equal to bn minus an b0, bn minus 1 minus n minus 1 into b0 so on dotted b1 minus a1 into b0. This is the C matrix. Okay, so we will take help from this value. At first we will write what is my b0 value. b0 is 1, because see, b0 becoming s to the b0 s to the power n plus b1 s to the power n minus 1 plus b2 s to the power n minus 2 in such a way. So b0 is numerator coefficient is s square, that at the available numerator coefficient is 1, at the numerator s to the power 1, and b1 is 3, and s to the power 0 coefficient is b2, that is 3. Similarly, at the denominator we will see highest power coefficient, that is s to the power 2, that is s square coefficient is a1 is here 2 and a2 is 1. That means here see all these things are available. The resulting is what? Because a0 is also 1, a0 is not needed here, and the resulting state space model is what? We will arrange that thing at the A matrix. How many variables will be available? 2 variables, x1 dot and x2 dot, and A matrix will be arranged in such a way. How can we arrange A matrix? That is, see, we will take help from this controllable matrix form. What is the controllable canonical form? So A matrix is nothing, that is 0 1 0 so on dotted 0 up to minus an minus minus 1 minus an minus 2 up to minus a1. So at the first column, first element will be 0, then 1. Okay, then rest will be minus an and minus an minus 1. So here see how 0 1 is remaining fixed for 2 dimension matrix, and minus a1 minus an and minus an minus 1 minus an is nothing, that is this one, an is nothing, that is 1, that's why minus 1 and minus a minus 1, that is 2 minus 2. Okay, so we may write the A matrix last row contains minus 1 minus 2 and first row is 0 1 and x1 x2. Already I told you that is x1 dot is equal to x2. See, x1 dot is equal to x2 means we are assuming y is equal to x1, that's why. Okay, and the input matrix is nothing, that is 0 1, because first element of the first column should be 0 and the last element should contain 1 when we will approach the controllable matrix form, because see this is 0 1. Okay, now see, and that is u, and the y matrix will be there maintaining that formula. What is the formula? That is bn minus an b0 and bn minus 1 minus an minus 1 into b0, that formula. So bn is nothing, bn is, what is my bn? That is, it should be generated bn minus an b0, an is nothing, that generates 2, and bn minus 1 minus an minus 1 into b0, it generates 1. You can apply those formulas and you can generate that thing, and d value is always 1, that's why the y matrix will be 2 1, y is equal to 2 1 C matrix, and x1 x2 2 variables plus u. Okay, another representation is the diagonally. How can you represent the state space representation in diagonal canonical form? Suppose the transfer function is given to you, g of s is equal to 2s plus 3 by s square plus 5s plus 6. So it is partial fraction is needed expansion, that is we may write 2s plus 3 by s square plus 5s plus 6 is equal to a by s plus 2 plus b by s plus 3. And after solving that thing, we have been generated a value is minus 1 and b value is 3, and we have two distinct poles for these. These poles are minus 2 and minus 3 respectively. So diagonal means all the p's, that is the poles should be arranged diagonal value. A matrix contains all the poles should be arranged in diagonal value, and rest elements will be 0. See, principal diagonal contains the p elements, that is pole. One pole is minus 2, another pole is minus 3. That's why see minus 2 minus 3, dimension is 2 dimension, that's why x1 x2, and rest elements are 0. And the input matrix, that is B, is always 1 1 unity matrix. And the C matrix, what is C matrix? What is the formula for C matrix? C matrix is C1, C2, so on dotted Cn minus 1, Cn. So we may write C1 is nothing. What is my C1? A1. A is minus 1. So C1 is minus 1 and C2 is 3. So this is the representation of the diagonal representation for a given transfer function. Okay. So transfer function to state space model is generated. Now state space model to transfer function we will see. Suppose the state space model is given to you, x dot is equal to ax plus bu and y is equal to cx plus du. A is already mentioned, a, b, c, d, and using Laplace transform, here dot is not visible, that's why x dot should be available, it is not visible due to some error. Okay, that is actually x dot state space model. So please keep in your mind. Then we are applying Laplace transform on both sides of the equation with zero initial condition. You may ask me, sir, why you are applying zero initial condition? Because our aim, we need to determine the transfer function. The basic definition of transfer function is that the ratio of the Laplace transform of the output variable to the Laplace transform of the input variable with zero initial condition. That's why. So when I am applying at the Laplace transform to the x dot is equal to ax plus bu, it generates with zero initial condition s x of s is equal to ax of x plus bu of s, which implies x of s is equal to si minus a whole inverse into b into u of s. Already I have been mentioned about this term si minus a inverse, si minus a inverse. Already I have been mentioned, I is the identity matrix. I depends on the dimension of A matrix. If it is 2 dimension of A, then I should be 1 0 0 1. If it is 3 dimension, then I should be 1 0 0 0 1 0 and 0 0 1. Okay, then we are applying Laplace transform with zero initial condition to the output equation y is equal to cx plus du, that generates y of s is equal to cx of s plus du of s, which generates y of s is equal to c. We are replacing the value of x of s. X of s is nothing, si minus a whole inverse into b into u of s. So I am replacing that thing, that is c into si minus a inverse into b, and du plus d. If d is available, then d, otherwise if d is null matrix, then that portion is vanished. That's why c into si minus a whole inverse into b plus d whole into u of s. Keep in your mind, you should not change the order of the matrix product, otherwise it will generate wrong result, because matrix multiplication does not maintain commutative property. A into b does not equal to b into a. So we can generate the transfer function t of s is equal to y of s by u of s is equal to c into si minus a whole inverse into b plus d. This is valid for SISO system, single input single output. If the system is MIMO, then C becomes C transpose only. Rest things are remaining same. That means T of S for MIMO system, it will be T of S is equal to C transpose of Si minus A whole inverse into B plus D. Okay. Now find the transfer function from the following state model of that. So if we are giving you x dot is equal to 0 1 0 0 0 1 and minus 2 minus 1 minus 2 minus 3 of x, and the input matrix contains B matrix 10 0 0 u, and y is equal to 1 0, that is C matrix contains 1 0 0 x. So our first job, we will evaluate what is Si minus A. Si minus A means that is I should be 3 dimension because A dimension is 3. Si minus A will be S minus 1 0 0 S minus 1 and 1 2 S plus 3. Then our job, we will evaluate what is Si minus A whole inverse, that is adjoint Si minus A by determinant Si minus A, and it will be generating the determinant with the adjoint, means the respective cofactor will be arranged and it will be the transpose, then adjoint will be determined. And after that we will evaluate that is the transfer function is T of S is equal to C into Si minus A whole inverse into B plus D. See, C value is 1 0 0, and this determinant is nothing, that is si minus a whole inverse term, and b is 10 0 0. This is 10 0 0. D is not available, that's why D is null matrix, which generates after matrix multiplication. It generates 10 into a square plus 3s plus 2 whole by divided by s cube plus 3s square plus 2s plus 1. Okay, now see system polls from state space model. Polls and check the stability of the following state space model. So if we are giving you x dot is equal to, all the dots are, I don't know why these dots are not highlighting. So x dot is equal to 0 2 minus 1 minus 3 for the matrix A, x plus 5 0 for the B matrix is 5 0 u, and y is equal to 1 0 c is 1 0 x. Then solution is si minus a is s minus 2 1 and s plus 3. The poles will be the determinant when equal to 0 it generates. Poles will be minus 1 and minus 2. The system is stable because it generates non-zero pole. That's why system is stable. Okay, from the state space model. Now the assignments are given to you. For the given state model, that is dx of t by dt is equal to ax of t plus b u of t, and y of t is equal to cx of t plus d u of t. Determine the transfer function of the above state model. Another question is, find the transfer function for the given state model, that is x1 dot by x2 dot is equal to minus 9 5 2 7 x1 x2 state variables plus b matrix is 8 minus 3 u of t, and y of t is equal to minus 9 2 x of t. Okay, and references are given, that is already I am mentioning from the first slides onwards. These two books are very good. You can refer from any other books also. I am following that thing. And okay, thank you. Today is up to this.